Hi everyone, this is Charan. This is regarding icp11. The goal is to make 4 changes on the unit architecture and to give the outcomes why we have chosen the 4 changes that we are supposed to run. Before going out with the changes from the given ICP, I could see the performance of the model on running is about 84.41 at the epoch 9. It has stopped early out of more epochs because of the learning parameters, because the loss is moved. So by using of the early stopping, it has stopped giving processing the further mode. So going to my changes, I've used the same implementation, but then I've used the unzip code, and couple of issues I faced during this is using the Kaggle's old API version that is complained about it, and I have to use this to re-upgrade and force install the Kaggle with no depth as the argument. Quickly showing before I run the model, quickly showing out about these values. As we can see, these are the 4 changes I made. First, changing the dropout values. The currently dropout values in the given is 0.1, which implies 10% of neurons not getting fired during training, but I've increased that to 30% to ensure our model is more robust towards the training data that we have provided. And the next change is changing the optimizer from Adam to RMS prop. This is because RMS prop has a unique ability of picking up the learning rate specific to the neuron. I believe using this kind of mechanism may help to grow the weights unevenly with, and which means there brings a non-linearity in how the weights are gonna update it back, or the back propagated in the neural network. So adding more convolution layers, this is another change I've done. So I've used more convolution layers at C7 layer. That's because most of the losses that we see appears while reconstructing based on the bottleneck features that we see. In order to arrive that, I wanted to see add the more deep learning convolutional layers to preserve more important layers at that layer, and also changing the function from ELU to ReLU. This is more or less ELU and ReLU are the same except the negative variants, but usually the ReLU is the go-to parameter in order to is a go-to function, activation function, in order to converge fast and also bring out more um, non-linear way of doing things by using ReLU. This is a mathematical representation of ReLU, and I've used ReLU all across the convolution layers. As we can see, the new models that I've built, or the new layers that I've created, is here. And I've changed the RMS prop as a optimizer. As we can see, this model took a little more than the earlier convergence at at ninth epoch in the given model, and shows validation of accuracy of 86.69. On the other hand, this one shows 84.41, which shows there is about 2% increase, close to 3% increase on the model by change of these parameters. So these are the few more from the given ask. The visualization is asked to map around 10. So I've picked up 10 random figures and did the segmentation imaging on the graph, as we can see these. So here are the conclusions, and here is the provided model that I'm showing. The accuracy for is about 84.41 from the run I've shown you here, and this is from 86.69 from the run I gathered here. As we can see, because of some of the reasoning that I had behind adding these layers and these hypermeasurements change, I could see there is a little improvement in the accuracy, close to 2.5 to 3%. I've rounded it off to 3% while noting the conclusions. Thank you. And I would like to show the run. As you can see, it is happening here. Once after this process completes, we can see the model running at the below layer. This is where the model is being built, and this is where it actually runs. Right, wait for a few more minutes for this to run. The model, it's almost about to finish this. It's about 3%. As we can see, the training is kicked off, and we'll eventually see the segmentation images that are created here. As we can see, the dice accuracy is converging quite fast. These are the certain images. Thank you.